Select the major product of the following reaction sequence. So if we look at our starting material, we see that this is a secondary alcohol. And we see that we've got two chiral centers. So the chirality is probably something we need to pay close attention to in this example. So we're going to take it stepwise. And so the first thing we're doing is we're taking this secondary alcohol and we're reacting this with TSCl, which is tosyl chloride. And so this is tosyl is shorthand for para-toluene sulfonyl, which is a mouthful. So let's go ahead and draw this. So we've got a methyl group on one side of a benzene ring, and directly opposite, we've got this sulfonyl chloride. So this portion of the molecule here is the tosyl portion. Or abbreviated TS, again for para-toluene sulfonyl, and then the Cl would be chloride. Okay, and then the pyridine is a non-nucleophilic base. So it is a nitrogen base that looks like this. So when we say it is non-nucleophilic, that means it can act as a base in terms of removing an acidic hydrogen, but it is not going to compete as a nucleophile. All right, so the first thing that's going to happen in this first step is your alcohol is a nucleophile. The sulfur of your tosyl chloride is electrophilic. So I'm going to redraw this structure of the tosyl chloride just because I don't think it's all that clear. So let's redraw this. All right, so this is electrophilic, this is nucleophilic. So your first step is going to be the attack of your alcohol on that sulfur, and it's going to kick off chloride as a leaving group. And so that means you will have attached this whole piece to your oxygen. And so this bond here, I said we're going to pay attention to stereochemistry. This bond hasn't changed because it's only the oxygen and the sulfur, and nothing's happened with this carbon-oxygen bond, so it should still be on a wedge. So we've got the oxygen, it's got a hydrogen, a positive charge, a bond to the sulfur, which then in turn has all of the rest of the stuff still bound to it, the double bonds to oxygen and the benzene ring. All right. And so this positive charge, that's an acidic hydrogen. So your pyridine, your non-nucleophilic base, can remove that. So we're going to carefully draw this whole structure. The methyl group hasn't changed. The bond to oxygen hasn't changed in terms of its orientation. We no longer have that hydrogen, but we do still have the bond to the sulfur, which has its two double bonds to oxygen, and then the benzene ring. So what we have here, this is a para-toluene sulfonate ester, but in general, it is a sulfonate ester. And what this is a good leaving group. So you can consider this to be about the same as what you would think of as an alkyl halide in terms of leaving group ability. So this is a secondary sulfonate ester. You can, in your mind, treat this as a secondary alkyl halide and use that when you're deciding what's going to take place in the second step. So in your second step, you've got sodium cyanide. So cyanide, that's a pretty decent nucleophile. It's not a really strong base. So you would expect in the second step, because you've got a secondary sulfonate ester, and we're going to say that this will react similar to a secondary alkyl halide as a key. And we're reacting this with cyanide, which is a good nucleophile, but not a strong base. Right, so putting these two pieces of information together, we're going to expect to see an SN2 reaction. Okay, so I'm going to draw the cyanide ion. There it is. And if this does an SN2 attack, Now we are involving this chiral center. We expect that this cyanide is going to attack from 180 degrees away from that sulfonate ester, which is going to invert the chirality at that carbon center. The chirality down here hasn't been affected by any step of the reaction, so we expect that that will remain the same. And so you can see that that is option C.